Hey everyone, welcome back to the channel. Engineer Empire here. I'm a software engineer turned corporate VP and head of technology. I dive into topics like engineering, finance, and business. If that interests you, please hit like or subscribe. Today I'm reacting to the most implausible tunneling method.
The original plan to get I-95 over the Baltimore Harbor was a double-deck bridge from Fort McHenry to Lazaretto Point. The problem with the plan was this. The bridge would have to be extremely high so that large ships could pass underneath, dwarfing and overshadowing one of the US's most important historical landmarks. Fort McHenry famously repelled a massive barrage and attack from the British Navy in the War of 1812, and inspired what would later become the national anthem. An ugly bridge would detract from its character, and a beautiful one would compete for it. So they took the high road by building a low road and decided to go underneath the harbor instead. Rather than bore a tunnel through the soil and rock below like the Channel Tunnel, the entire thing was prefabricated in sections and installed from the water surface above, a construction technique called immersed tube tunneling. This seems kind of simple at first, but the more you think about it, the more you realize how complicated it actually is to fabricate tunnel sections the length of a city block, move them into place, and attach them together so watertight and safe that eventually you can drive or take a train from.
That does sound interesting. I'm curious to see how long these segments are, but agreed, you'd either have to make a likely infeasibly long tube, effectively, that is ginormous in scale, such that cars and other things can go through it. And then that kind of goes from one end to the other. Or the more likely option, I'm suspecting, is that they have to do it segment by segment. And so you have to make sure that, like, adding these two things together would not have a leak in between. So I guess, like, if you had two straws and you were trying to connect them underwater, but make sure no water got into either straw, that sounds very challenging in and of itself.
One side to the other. Immersed tube construction makes tunneling less like drilling a hole and more like docking a spacecraft. Materials and practices vary across the world, but I want to try to show you, at least in a general sense, how this works. I'm Grady, and this is Practical Engineering. One of the big problems with bridges over navigable waterways is that they have to be so tall. Building high up isn't necessarily the challenge, it's getting up and back down. There are limits to how steep a road can be for comfort, safety, and efficiency, and railroads usually have even stricter constraints on grade. That means the approaches to high bridges have to be really long, increasing costs and, in dense cities, taking up more valuable space. This is one of the ways that building a tunnel can be a better option. They greatly reduce the amount of land at the surface needed for approaches. But traditional tunnels built using boring have to be installed somewhat deep into the ground, maintaining significant earth between the roof of the tunnel and the water for stability and safety. Since they're installed from above, immersed tube tunnels don't have the same problem. It's basically a way to get the shortest tunnel possible for a given location, which often means the cheapest tunnel too. That's a big.
Something else that I'm now realizing as he's going through this example is you'd also have to be very mindful of water levels, because especially like in today's world where water levels are generally rising, you'd also have to be mindful of the fact that if you try to go for the shortest distance, then that's exactly where you get closer and closer to the water line. And so you'd have to be thinking about how do you prevent water from eventually spilling over and into the tunnel itself.
Because tunnels are just about the most expensive way to get from point A to point B. Anything you can do to reduce their size goes a long way, and there are other advantages too. Tunnel boring machines make one shape, a circle. It's not the best shape for a tunnel in a lot of ways. Often there's underutilized space at the top and bottom, excavation you had to perform because of the machinery that is mostly just a waste.
So I do agree with that at face value, that obviously the ideal shape would basically be a rectangle for driving purposes, as he sort of demonstrated here. The thing that I don't think he's quite covered here, though, is the fact that there are other things that you need to have. So, at least from my basic understanding of what you would need to be mindful of here is one thing being like electricity, as an example. You need to have electrical lines. There's usually lights within a tunnel because obviously a tunnel would be dark inherently, especially a man-made one. And so there's no openings above it to let sunlight in or anything else. So you need lighting. You need electricity for that lighting. You usually also need different segments and space to perform maintenance on the roads and other things, as well as air. Air is probably the most important thing that you'd have to think about, which is how does airflow get in and out, especially when cars have exhaust fumes, etc. And so, at least to my understanding, while not necessarily the ideal shape, I think some of this extra space is used for those purposes. So I don't think there's ever a scenario where you can just like perfectly draw a rectangle for exactly the size shape that you would need for vehicle traffic and then just make that as the tunnel. So I'm curious if he's going to cover that as part of this.
Immersed tubes can be just about any shape you need, making them ideal for wider tunnels like combined road and rail routes where a circular cross-section isn't a good fit. One of the other benefits of immersed tubes is that most of the construction happens on dry land. I probably don't have to say this, but building stuff while underground or underwater is complex and difficult work. It requires specialty equipment, added safety measures, and a lot of extra expense. Immersed tube sections are built in dry docks or at a shipyard where it's much easier to deliver materials and accomplish the bulk of the actual construction work. Once tunnel sections are fabricated, they have to be moved into place, and I think this is pretty clever. These sections can be enormous, upwards of 650 feet or 200 meters long, but they're still...
That is quite long. It is actually very impressive that they're building these outside of the water and then placing them in and then connecting them. And I think it was a great point that he mentioned about extending that rectangle beyond, because that's exactly what you'd want for railways or other methods of transportation as well. Whereas like the circle you have to make just has to keep getting bigger and bigger, and potentially, while some of that space could be utilized for other purposes, more and more of it would go to waste the more lanes you effectively want to have.
Mostly air. So if you put a bulkhead on either side to trap that air inside, they float. You can just flood the dry dock, hook up some tugboats, and tow them out like a massive barge. Interestingly, the transportation method means that the tunnel...
That is interesting. I'm assuming that these are airtight on both ends of the segment, and that's what allows them to float, and also allows them to actually be reasonably reattached.
Segments have to be designed to work as watercraft first. The weight, buoyancy, and balance of each section are engineered to keep them stable in the water and avoid tipping or rolling before they have...
I'm actually curious. I think this makes sense because obviously that's how you get them in place. But I'm curious how they then stay in place below the water if you are inherently trying to make sure that they are buoyant to begin with.
To be stable as a structure. Once in place, a tunnel segment is handed over to the apparatus that will set it into place. In most cases, this is a catamaran-style behemoth called a lay barge. Two working platforms are connected by girders, creating a huge floating gantry crane. Internal tanks are filled with water to act as ballast, allowing the segment to sink. But when it gets to the bottom, it doesn't just sit on the sea or channel floor below, and this is another benefit of immersed tube construction. Especially in navigable waterways, you need to protect a tunnel from damage from strong currents, curious sea life, and ship anchors. So most immersed tube tunnels sit in a shallow trench, excavated using a clamshell or suction dredger. Most waterways have a thick layer of soft sediment at the surface, not exactly ideal as a foundation. This is another reason most boring machines have to be in deeper material. Drilling through soft sediment is prone to problems. Imagine using a power drill to make a nice clean hole through pudding. But at least in part due to being full of buoyant air, immersed tubes aren't that heavy. In fact, in most cases, they're lighter than the soil that was there in the first place, so the soft sediment really isn't a problem. You don't need a complicated foundation. In many cases,
So he hasn't quite referenced erosion here. I guess that would be another thing I'd be curious about for softer sediment beds for where you actually use as a foundation for one of these tunnels is I would assume and imagine that as the riverway or waterway that you're kind of setting up this tunnel for, there's the possibility of that sediment kind of being moved around and the tunnel itself then inherently moving as well.
It's just a layer of rock or gravel placed at the bottom of the trench, usually using a fall pipe, like a big garden hose for gravel, to control the location. This layer is then carefully leveled using a steel screed that's dragged over the top like an underwater bulldozer. Even in deep water, the process can achieve a remarkably accurate surface level for the tunnel segments to rest on. The lowering process is the most delicate and important part of construction. The margins are tight because any type of misalignment may make it impossible for the segment to seal against its neighbor. Normally, you'd really want to take your time with this kind of thing, but here, the work usually has to happen in a narrow window to avoid weather, tides, and disruption to ship traffic. The tunnel section is fitted with rubber seals around its face, creating a gasket. Sometimes the segment will also have a surveying tower that pokes above the water surface, allowing for measurements and fine adjustments to be made as it's set into place. In some cases, the lowering equipment can also nudge the segment against its neighbor. In other cases, hydraulic jacks are used to pull the segments together. Divers or remotely operated submersibles can hook up the jacks, or couplers, just like those used on freight trains, can do it without any manual underwater intervention. The jacks extend to couple the free segment to the one already installed, then retract to pull them together, compressing the gasket and sealing the area between the two bulkheads. This joint is the most important part of an immersed tunnel design. It has to be installed blindly and accommodate small movements from temperature changes, settlement, and changes in pressure as water levels go up and down. The gasket provides the initial seal, but there's more to it. Once in place, valves are opened in the bulkheads to drain the water between them. That actually creates a massive pressure difference between one side of the segment and the other. Hydrostatic force from the water pushes against the end of the tunnel, putting it in even firmer contact with its neighbor and creating a stronger seal. Once in its final place, the segment can be backfilled. The tunnel segment connection is not like a pipe flange where the joints are securely bolted together, completely restraining any movement. The joints on immersed tunnels have some freedom to move. Of course, there's restraint for axial compression since the segments butt up against each other. In addition, keys or dowels are usually installed along the joint so that shear forces can transfer between segments, keeping the ends from shifting during settlement or small sideways movements. However, the joints aren't designed to transfer torque, called moments, and there's rarely much mechanical restraint to axial tension that might pull one joint away from the other. So you can see why the backfill is so important. It locks each segment into place. In fact, the first layer of backfill is called locking fill for that exact reason. I don't think they make underwater roller compactors, and you wouldn't want strong vibrations disturbing the placement of the tunnel segments anyway. So this material is made from angular rock that self-compacts and is placed using fall pipes in careful layers to secure each segment without shifting or disturbing it. After that, general backfill, maybe even the original material if it wasn't contaminated, can be used in the rest of the trench. And then a layer is placed over the top of everything to protect the backfill and tunnel against currents caused by ships and tides. Sometimes this top layer includes bands of large rock meant to release a ship's anchor from the bottom, keeping it from digging in and
Interesting. Also in this example, they are still showing that there's basically like some digging out of the sediment here. So I think that kind of answers my question on what happens with the sediment that could be floating away, is that they actually go deeper into it and then kind of cover on top again. In order to avoid too much erosion from impacting this tunnel.
damaging the tunnel. Once a tunnel segment is secured in place, the bulkhead in the previous segment can be removed from the inside, allowing access inside the joint. The usual requirement is that access is only allowed when there are 2 or more bulkheads between workers and the water outside. A second seal, called an omega seal because of its shape, then gets installed around the perimeter of the joint. And the process keeps going, adding segments to the tunnel until it's a continuous open path from one end to the other. When it reaches that point, all the other normal tunnel stuff can be installed, like roadways, railways, lights, ventilation, drainage, and pumps. By the time it's ready to travel through, there's really no obvious sign from inside that immersed tube tunnels are any different from those built using other methods. This is a simplification, of course. Every one of these steps is immensely complicated, unique to each job site, and can take weeks to months and even years to complete. And as impressive as the process is, it's not without its downsides. The biggest one is damage to the sea or river floor during construction. Where boring causes little disturbance at the surface, immersed tube construction requires a lot of dredging. That can disrupt and damage important habitat for wildlife. It also kicks up a lot of sediment into suspension, clouding the water and potentially releasing buried contaminants that were laid down back when environmental laws were less strict. Some of these impacts can be mitigated. Sealed clamshell buckets reduce turbidity and mobilization of contaminated sediment. And construction activities can be scheduled to avoid sensitive periods like migration of important species. But some level of disturbance is inevitable and has to be weighed against the benefits of the project. Despite the challenges, around 150 of these tunnels have been built around the globe. Some of the most famous include the Øresund link between Denmark and Sweden, the Busan-Goje Tunnel in South Korea, the Marmaray Tunnel crossing the Bosphorus in Turkey, of course the Fort McHenry Tunnel in Baltimore I mentioned earlier, and the BART Transbay Tube between Oakland and San Francisco. And some of the most impressive projects are under construction now, including the Femern Belt between Denmark and Germany, which will be the world's longest immersed tunnel. My friend Fred produced a really nice documentary about that project on the B1M channel if you want to learn more about it, and the project team graciously shared a lot of very cool clips used in this video too. There's something about immersed tube tunnels that I can't quite get over. At a glance, it's dead simple, basically like assembling Lego blocks. But the reality is that the process is so complicated and intricate, more akin to building a moon base. Giant concrete and steel segments floated like ships, carefully sunk into enormous trenches, precisely maneuvered for a perfect fit while completely submerged in sometimes high-traffic areas of the sea, with tides, currents, wildlife, and any number of unexpected marine issues that could pop up, and then you just drive through it like it's any old section of highway. I love that stuff.
Thank you for watching. If you've enjoyed what you've seen, please hit like or subscribe. I'll see you around.